So hello, everybody. And thank you, Andy, for the introduction. Thank you to AdaCore and Capgemini Engineering for the invitation, which I must admit I was really delighted by. I know quite a few people, whether it would be Andy or the former Altam people, and then through my being director of the Research Institute in Verified Trustworthy Software Systems. And I loved getting an invitation that was not about my organization of things, but actually about my research. I tend to make a point of not talking very much when I'm being in the directorship role. And so it's lovely to have this invitation. But in particular, I very much wanted to put this in the wider context of the Research Institute. So I've given it a general title, and I will be talking in quite a general way, but also I will be totally biased on my research, if you don't mind today. I'm going to talk about a particular type of technique of doing verified specification. And it's one I'm sure you know quite well. One has the notion of a target language. It could be C or JavaScript or many languages. We compile that to an intermediate representation. And whereas the specification of programs is done at the abstraction of the target language and is hopefully understandable by code developers associated with the target language, the actual program verification is done in some intermediate representation, quite often a go-to language that's lost all the structure of the target language. I'm only going to talk about this particular type of diagram today. There's lots of other ways of doing it. For example, one key one is that the analysis is done at the level of the target language. I'm not going to get into pros and cons of which approach. There's lots of people that use this approach. So in particular, there's a lot of work in industry on lightweight bug finding, for example, in the Facebooks and the Amazons, that sort of place. But there's also just beginning to be a lot of work on verification. Now, it's familiar in for safety critical software, but now it's pushing in to the more general place of verification for, at the moment, the specialist developer who is not necessarily doing safety critical systems. One key one is CBMC, if you think of it as this bounded verifier, where it's being used a lot inside, for example, AWS. Something like something like CBMC is very much at the level of results in first order logic about the variable store. It does give information about the heap, but not so very much. And it's a bounded model checker. There's Frame-C, again based on first order logic, and used a lot inside the French alternative energy and atomic authority. And that is, these are well known, have been around for a while. And then there's this new style of work, where this new style of work is based on something called separation logic or variance on that theme. And there the idea is that one is working very much with the heap, with the resource associated with the heap, and trying to analyze properties associated with bits of the heap. And examples include Verifast used for C and Java, Viper, and that's Viper for Rust, Python, and Go. And the one I'm working on, which is Gillian for C, JavaScript, and Rust is on the way. So I point out Daniel Kronig does CBMC, Bart Jacobs does Verifast, and Peter Muller does Viper. When I looked up Framer C, there was this whole team of people, so I couldn't find a photo. Please, somebody tell me who to do if it makes sense. Now, if we're going to do specification in a target language, we're first going to need to know, and their analysis at this intermediate representation, we need to know what we're talking about. So actually, we need a definition of the language. And there's very many possibilities. There's English and pseudocode standards, and often quite standardized. And the examples include C and JavaScript standards. There's a standard in the sense that the language is a particular implementation. And that's the way it works with Python and Rust. And then coming along a bit later, but just about getting into the standardization now, is formal specification. So we started with ML of Milner, C-Lite of the CompCert project, going all the way to some work that I did on JS Cert that was my first introduction to Andy and that crowd, and to the new stuff such as ASL, the Architecture Specification Language, and WebAssembly. And I'd actually, just if you don't mind, going to do a little detour and talk about WebAssembly for a moment. And the reason for this is that I'm actually quite excited. So we worked here, and then Conrad Watt, who was in Imperial and now is in Cambridge, worked here using the methodology that we first set up. And as a brief history, we have WebAssembly with a formal draft done in PLDI 17. The new stuff is, the aim was an industry standard that had a formal specification. And this guy, Anders Rosberg, set that agenda rolling with his co-authors. Conrad came along with an Isabelle mechanized specification that actually found things that needed changing in the PLDI 17 publication. So both in the formal specification and in the results that were approved, he went right to the heart of it. Now we're at WebAssembly 1.0, so whereas this was a draft, now we're in a real W3C recommendation that happened in 2019. My community loves this language, and we've given them an award. And just this year, we've got mechanized specifications of what we're calling WASM Cert in Isabelle and Coq. The Isabelle stuff absolutely is Conrad. This stuff, actually, bizarrely, is a mixture of a gang of mine and Conrad and Jean from Cambridge. And it was absolutely random how these people came together. In particular, Martin Baudin was on the JS Cert project and then was a postdoc of mine. The only reason why we're doing this is because Rao came along saying, I want experience with a theorem prover. And we had a nice little thing to give him. So this is how random this stuff is at the moment. So for both Isabelle and Coq, we've done mechanized inductive definitions of WebAssembly 1.0. We have got the formal and then mechanized industry standard, which I'm excited by because with the JavaScript work, we had to stop because the language doubled in size. It's too hard. We've got associated reference interpreters that are proven correct with respect to Isabelle and Coq, with an automatic extraction into OCaml. The Isabelle one has been tested. The Coq one is on the way to being tested. We've got type soundness proofs. And then Watt, with Stefan in UCSD, has done some cryptography-focused language extensions to be published this year, and they're in process of being standardized. Conrad Watt's interesting. He's on the committee, so he's right embedded in the heart of this work. The two main formalists are Conrad and Andreas, but I think that's probably changed now. There's probably lots. The future. So Conrad is doing a fast, provably correct reference interpreter for industrial use. And Rao is doing Iris WASM with the Aarhus gang and Conrad and me, which provides mechanized program verification using the Iris framework in COC. But my main question, especially for this audience, is how do we provide a mechanization that keeps pace with future formal extensions? So at the moment, Conrad's opinion is that they can keep pace with the formal extensions, because by the time they've done all the fighting to get the extension properly recommended, the formalism has happened. That's not the case with concurrency, because concurrency is hard, but the other stuff, it's basically not doing too badly there. But then what does it mean to put a mechanization on top of it and to keep it? Conrad wants to work in academia, so he's got to be doing new things. Rao's on the Iris WASM. Martin's gone to Grenoble. Jean is now an academic in Aarhus. So, you know, we're thinking quite hard about it in this ad hoc, almost amateur way of trying to cobble some people together. But actually, this is viable right now. And the question is, what does it mean to do it? Don't know the answer to that. But now back, that was an absolute little detour. I'm back to my the main part of my talk. So we have the language specification, and bizarrely, it wasn't by design. We're working with C, JavaScript, and Rust. And for C, we have a formal specification of the language. For JavaScript, we have pseudocode as the standard. And for Rust, we have an implementation. So always we've been wondering, what's it mean to do this trustworthy verification in the context that we're having a compiler from the target language to the intermediate representation. So for C, we do certified compilation. And in particular, we use the verified CompCert compiler initiated by Xavier Leroy. And then Greg Morissette was in this world saying, we must get the types to be preserved during compilation. And Andrew Appel in his verified toolchain is saying, and we must get the analysis to work through the compilation. So we're sort of in this world, and that's where we will be using CompCert. For JavaScript, we had to actually work out what on earth we were going to do. And because we'd done a mechanized specification of JavaScript in COC, we understood the standard very well. So we were able to write a compiler that in our eyes we could think of as trustworthy. And the way that we were expressing this is that it preserves the memory model, because for the point of view of analysis, you absolutely want to analyze the memory model. This is the point of what we're doing. You want to preserve the semantics. This is nothing clever at all about performance. This is only about getting rid of control flow by translating it to a go-to language. Interestingly, we absolutely have to work very hard so that the specification that's presented at the level of the target language is also present at the level of the intermediate language. We want to be line by line close to the standard and well tested so that we have some justification to say that we are trusted in the context that we didn't want to do full mechanized compilation certification. And I want to introduce to you, I don't know whether you know her, Suk-Young Woo, given here. You know, she has just published something called GISET. And she's done an absolutely lovely thing. It was something we knew about, but we didn't have expertise for. And I'm so delighted that she's done it, which is you've got the English pseudocode of the standard. She has automatically extracted the associated implementation in a little meta language of the standard. And she's done that by doing natural language processing, observing the pattern that's going on in the pseudocode of the standard. So whereas we could do, we did ECMAScript 5 strict, she's gone all the way right up to the double the size new standards, very much very near staying up with the standards. So what's the right way to think here? From my point of view, as I'm a formalist, I like to have things formal and then think about how to get the English descriptions and the pseudocodes descriptions. But absolutely starting off from the pseudocode, because that's the natural way for the committees to work, and then pulling out the quite systematic reference interpretation is really quite a lovely thing, I think. And then we have the analysis going on at the intermediate representation. So as I've emphasized, there's quite different ways of doing it. The way I do it is based on based on a separation logic of O'Hearn, like similar to Verifast. Viper does it a slightly different way, but not so very different. And these are the guys involved. I should have said at the beginning, Petter is currently on chat. I hope he has said hello to himself in chat. And please ping in with questions as we go, because I wonder how much time there will be at the end. We have Petter, Jose, Sasha, and myself. So for our intermediate representation, we have a go-to language. And we have a first-order solver underpinned by the Z3 SMT solver. Many people use this style. We do modular analysis, starting off from a core symbolic execution, building on top of that verification, and building on top of that something called by-abduction, which for those of you who know, it's a technique for making the Facebook info stuff work automatically for lightweight bugs. We're going to focus on verification in this talk. Now, there's something that's very different from our competitors is, well, this modular analysis for a start, but also fundamentally the parametric nature of our work. So in particular, our idea is the compiler is not altering the memory model. So the memory model of the target language is the memory model going into our intermediate representation. We've got two models, a concrete model for testing, a symbolic model for analysis, and correctness results between them. As I said, I will focus on verification, in particular, starting off with basic memory actions and building up core predicates, as I'll explain to you now. And this is work published this year. Previously, it was published in PLDI, the first lot that I've just explained, now CAV. So we're starting off with memory. We're going to think about memory in a compositional way, which is different from the previous work we've been doing. And we start off with fundamental units of the target language memories. For now, just think of tiny heap cells, and we'll get more complicated as we go along. So memory is built up of these tiny units. And these tiny units are going to be described using these core predicates. And associated with core predicates are consumers, which frame off the resource described by the core predicates. And we have producers, and producers frame on core predicate, the core predicates resource. Core predicate resource means the resource described by the core predicates. And the core predicates have this form. A Greek name, because we're formalists, sorry for those who are not so happy with that, and input parameters and output parameters. Input parameters are enough to find all parameters in the sense that we have a parametric unification algorithm. So we have the memory we're working with, and we're trying to unify the memory with respect to a core predicate, where we have symbolic inputs, meaning logical variables that we're trying to instantiate with the current memory, which is also symbolic. And we are working with the in parameters. That is enough. The out parameters can come for free. And let me show you this by an example. If we think of a cell block offset cell assertion coming from C, then we've got location and offset that are the in parameters. And when you know these two, you absolutely know what the value is. The value is the out parameter. It can be found once you've got the int. And from these core predicates, we can build up assertions in the other underlying assertion language of our program logic. So we have user-defined predicates, just as simple examples, things like linked lists, that sort of thing. We have, they can get very complicated structures. We have pure assertions coming from first-order logic, and we have separating conjunctions. So basically, we've got this bag of stuff, starting off with core predicates. And we have this parametric definition of satisfiability in terms of producers and consumers. And what that does, it gives us a parametric way of handling function specifications, which is the key to sequential, for compositionality of sequential separation logic. So if we have a usual Hoare triple, you're looking like this, where this is the precondition and this is the postcondition. This little precondition needs to be matched to the current state, i.e. a little bit, it's going to be matched to a part of the current state. So we're on function specifications, and in particular, we're matching the precondition to the current state. We do it by consuming the precondition, taking it off, and then producing the postcondition using the bindings that we've got from the parametric unification algorithm. And we have parametric correctness results that requires minimal proof effort for the user, actually, if you wish. I wish, because I'm a formalist, but others might not wish, they just might want to get on with things. But in particular, those are given by lemmas per instantiation. So I'm just going to now describe a little bit about the instantiation. I'm going to have to go through this a bit quickly, I'm afraid. So I'm going to talk about C. This is simplified C. So in particular, in our implementation, we've done an awful lot of the bells and whistles of the C memory model. Here, we sort of published, and I talk about a simplified one, partly because I can get the key points across, and partly in the paper, I show quite a similarity between this work and the work of JavaScript. So there's a real resonance between the two things. So in particular, I want to emphasize we have concrete memory and with location and blocks. The block contain block contents and block bounds. And there's a well-formedness condition that when you've got a location offset pair, that offset is a natural number that absolutely can't go beyond the bound. And there's various places where you can have information that's missing because you're in compositional land. And what I mean by this, if we take a function specification, that function specification might be, the function might be doing something like putting a value in a location and an offset, i.e. it's only working with that tiny location offset cell, doesn't care how big the bound is, and it doesn't care about the rest of the details of the bound. So the function only needs the little bit of resource needed to do its job, even though the memory has much more. And also, I just want to emphasize that we've got locations with the ability for locations to be freed, so that when you do use after freed, you get the appropriate error. Symbolic memory is much harder in the implementation for performance reasons. Here, it's just a simple lifting of the concrete memory to symbolic expressions. We have core predicates, which are the block cell, the block bound, and the freed block. And with this, we have explicit negative information about cells not being in a bound, about locations being freed, and cells not being in the bound. We have user-defined predicates automatically generated for C structs. And what that means is that the C structs from the target language is getting pulled into information in the intermediate representation. I don't have time to talk about this. This is the tiny consumer for the cell. But in particular, sometimes you have missing information. Sometimes you have error information. I'm very much thinking about it as error information, not undefined behavior. So I can give information back to the code developer that they've done use after freed or buffer overrun. One more chunk of slides, I want to talk about Gillian in practice. We have done some AWS Encryption SDK message header code, in particular in JavaScript and C. And the current approach, everybody does concrete testing, and the people in AWS, and I think this is getting common, do runtime correctness assertions, written in first-order logic. In AWS C, they also do bounded model checking. And for example, you see bits of stuff here in first-order logic saying some conditions about the bound. So our first project was just to do a tiny thing, which is the message header deserialization module with 2,000 lines of code for JavaScript, about 1,000 lines of code for C, uses lots of features in both languages. All we're doing is a list structure. It's a dynamic list structure, and we can describe it using first-order abstractions. We can link those first-order abstractions to abstractions in separation logic in the context of assertions describing JavaScript memory and C memory. We can prove lemmas about all abstractions, and we can specify and verify these functions of this deserialization module. Here we found bugs, and also here was hard because there was a lot of dynamic list length going on. Just to show you a little bit of what was going on, it took us this amount of time, and well, there's way too many annotations for this to be truly viable. But let me break it down slightly. This lot was to do with the data structure. You've got lots and lots of functions. This lot is reused for all of them. Then this amount of code for C, this amount of code for JavaScript. We need to analyze that better to work out how to do less annotations. And this is the sort of thing that we're doing. I'll leave that. We've done the verification. we found bugs, including one that looked actually quite serious in terms of buffer overrun. And another to do with they didn't get the specification, the mathematics quite right. We've also substantially improved Gillian. So going from a tool that was good, really actually quite good for an academic tool at doing data structure algorithms, to a tool to doing real world code, really helped us in our development of Gillian. We loved that learning curve. It's the first time we believe that industrial JavaScript code has been fully verified. And it's the first time that abstractions used for the same abstractions are used for languages as different as these two. So we're quite enjoying this space of exploration. Some of you will know that there's been some recent work by O'Hearn on incorrectness separation logic to do with bug finding and emphasizing errors rather than working with the full verification, rather than working with specific under-approximating specs for specific errors. We can do this easily. We were in over-approximation land and precise land, or exact land. Pete's in under-approximating land, and a special case of under-approximating land is that exact land. So we've found ourselves resonating very closely with him. We haven't done full analysis of by abduction yet. We've done the basics. And we're absolutely on Gillian Rust at the moment. Sasha's firmly on that, and along with very many other people in our sort of world. And we would like to be on language interoperability and concurrency, which is my love in a different, with a different hat on. So thank you. I'm not sure whether there's time for questions, but what I would like to do is run the code, the verification of the code of the deserialization. In particular, this is the JavaScript one. This is 200 lines of code. It will take about 30 seconds. The C one takes about 3-4 minutes because the C code is 1,000 lines and because the memory model is really very subtle. Thank you for your attention.
Thank you very much, Philippa. Just while that's running, a quick question. What's the timescale for Rust that someone has asked in chat?
So we don't know. In particular, we are because we've done Gillian C, we think we can do unsafe Rust quite well, and we have to justify that. At the moment, we are at the level of what's the memory model, what's the compiler. Sasha has to finish at least something in a year's time because he has to write up. He's also going to be an intern in the Rust verification team at AWS next summer, which will mean he'll have a huge learning curve. And how on earth is he going to finish his thesis by March the following year? Who knows? But that's his timeline. And then we have to work out how long it will take. We'll be able to do some things quite soon. I mean, it will be fantastic if we get a publication out in a year, but that won't be on very mature stuff. That's where it's at.